I'm going to not introduce myself and get started with a second lecture, which will go a bit more into neural networks, but staying at a fairly conceptual level. You'll see more about algorithms, like especially the optimization part, this afternoon with Léon Boutou, and tomorrow with Hugo La Rochelle. But today it'd be more about the theoretical motivations for deep learning. So I guess you're here because you've heard about deep learning, and many of you have already played with these algorithms. And what are they about? Basically, deep learning is about learning representations, and in particular learning multiple levels of representations. And the idea is that these multiple levels of representation correspond to multiple levels of abstraction, and presumably, as I'll try to convince you, if we're able to do a good job of capturing these high-level abstractions, we can generalize well. And this is, of course, correlated with the amazing results that have been obtained in computer vision, object recognition, object detection, and speech recognition, and more recently, fairly impressive progress in natural language as well. So as Pascal was saying, the evolution of systems that can be used to answer questions and that we want to be more intelligent can be traced to this idea of incorporating learning and then incorporating representation learning and then multiple levels of representation. So in the old days of AI and symbolic machine, not machine, symbolic AI, basically the knowledge about the world that we wanted to put in the machine was provided by the humans, the experts. That's why they call these expert systems. And in a sense, we built a function from input to output using a hand-designed program that had two parts, the facts and the logic that allows to combine those facts to answer questions. Then came classical machine learning, which tried to solve simpler problems than the classical AI problems, not trying to do the full AI, but just doing something much simpler like pattern recognition. But it relied on hand-designed features like Pascal was telling you about. In fact, if anybody, I'm sure there's many of you here who have played with machine learning, tried machine learning, especially in an industrial setting, and most of the time that you guys have spent is probably to design the input of the machine learning system. And then we use some kind of generic, say, classifier to produce the output. So that's what machine learning has been for many years. And continues to be in many applications, a very crucial part to do this hand design of input features. Neural networks have been there as long, and the sort of standard one hidden layer or two hidden layer neural nets you can think of as, in addition to having a linear classifier on top, having this layer of features that are learned automatically at the same time as the classifier. And deep learning is just going further with this idea and saying, oh, we can have multiple levels of features composed on top of each other in order to come up with our final solution. Okay, so what I'll try to tell you about in the rest of this lecture is why this kind of approach may be working so well. And I don't claim that I have all the answers. There are many reasons why some of these systems are working, and some of them I won't touch about, like some of the priors that come into convolutional nets that will be discussed by other lecturers. But I'll talk about some of the basic general ingredients that I think explain part of the success of these deep learning systems. Before I get there, let me just step back a little bit and tell you about how we might build really complicated systems for AI. And how this is related to, how this question is related to a famous result from machine learning called the no free lunch theorem. So what I think are the basic ingredients for successful machine learning, especially towards AI, are the following. You need lots and lots of data. That's number one, and Pascal mentioned it, and why do we need lots and lots of data? You have to understand why. We're trying to build a system that's going to take decisions, and in order to take good decisions, which is what basically intelligence is about, you need a lot of knowledge, right? So an AI system or something that's solving a complicated task needs a lot of knowledge about the task that it's trying to solve. Where is that knowledge going to come from? Well, it either comes from humans who put it in or from data. And the machine learning part is about extracting knowledge from data. That's what machine learning is about. And if we want to learn a complicated task like understanding language or images, because these tasks are fairly complicated, we're going to need a lot of data, unless we already know how to solve that problem, and then we don't need that. But typically we don't know enough, and that's why we're going to be using machine learning. Now, as a sort of a corollary to this, it's not enough to have lots of data. You need to have a family of functions or model that's rich enough to represent that complicated function, to represent all that knowledge, right? So the knowledge comes in the form implicitly in the data, but then we have to translate that knowledge into something that we can use for taking decisions. That's our model or our neural net. And of course, we have to store that knowledge somewhere, that it starts from the data, it goes into a model. So the model has to be big enough, flexible enough. It can represent the kind of complicated function you need for your solving your task, right? So for sure we need these two things. Now, some people thought that might be enough. I don't think so. And a lot of what I'll be telling you about later is about the third ingredient, which you can basically think about as additional prior knowledge. And in particular, I'll talk about the curse of dimensionality and how it's a challenge and how we might get around it using some of the priors that come with most deep learning algorithms. All right, so this is going to be the subject of much of my presentation today. That third part, right? So given 1 and 2, data and powerful, flexible family of functions is not enough. We're going to need something else, which is fairly general knowledge about the world, but that's going to be necessary to get good generalization. Classical nonparametric statistics works with 1 and 2 and a very weak prior, which is called a smoothness prior, which I'll explain a bit later. But it's not enough. All right, so I guess I already said much of this. In order to get the knowledge, we need data and we need to learn. We need learning algorithms. And learning algorithms involve two things. Priors, so in other words, some kind of preference over the set of functions. Pascal talked about choosing a parametric family of functions, but you could be a bit more subtle, saying, well, there's some functions I prefer more than others. Like if we use regularization technique, it says some of those functions I prefer, some I prefer less, but maybe I'll end up choosing these. And you need some optimization techniques because choosing a function in an infinite set is potentially intractable, but some approximation or some search method will be required. Now, to get the machine learning to work, Pascal told you about generalization. This is really central, of course, in machine learning. But one thing he started talking a bit about, which I'll come back to, is a kind of geometric interpretation of what generalization means. So for people who know a little bit about probability, the way I like to think about it is generalization, the game of generalization is a guessing game. And it amounts to guessing which configuration of the variables of interests are good, are likely. So you can think of it like, guessing where probability mass should go, should be concentrated. I'll come back to that notion in my slides. And this kind of geometric view of generalization is interesting because it also connects with another important idea in machine learning and statistics, which is the curse of dimensionality. And again, I'll try to explain this, but basically what happens is we're dealing with these high-dimensional random variables like pixels, like sequences of characters, like acoustic signals. And because there's so many dimensions, and each dimension can take many values, maybe even just 2 already is going to be a lot, because 2 to the power 1,000, which are the number of images of 1,000 pixels with binary pixels, is already huge. Is already much too large to be able to enumerate, and we're not going to have enough data to consider all of those configurations. So for most configurations, we're going to have 0 data to tell us what the right answer should be. That's the problem, right? In the 2D, simple 2D case that Pascal showed, it looked like generalization is easy. But in a high-dimensional space, generalization looks almost impossible. But yet we have algorithms that do a decent job. So how can we potentially deal with this curse of dimensionality? And one of the big ideas that I've been trying to sell in many of my papers for the last almost the last decade is this idea that in order to defeat the curse of dimensionality, we want to figure out how the data was generated, to understand the explanatory factors that explain that are the causes of what we're observing. If we could do that, of course it's a tall order, then we would basically be making sense of the data and we'd be able to make very good predictions on new examples. That's of course a very ambitious program, and I think that what we're currently doing in deep learning is a step in that direction. We have by no means solved this problem. This is what science is trying to do, right? We're trying to make sense of the world by doing experiments and building theories that explain what we observe. So machine learning is basically kind of automated science. You can think of it like this, but on a scale where we're looking at lots and lots of data. All right, so let's go a little bit deeper into these questions. But first, let me go back to this notion of the curse of dimensionality and why the classical nonparametric methods like nearest neighbors that Pascal talked about don't cut it. Why they are really hurt by the curse of dimensionality. Right, so remember I said the curse of dimensionality arises because we have many configurations of the random variables. So if you have only one random variable, say a one-dimensional thing, and we're trying to learn from it, like to predict which values are likely or what y to associate to a given value of x. Where so these are the different values of x. We could bin the x's. We could break the input into say 10 different values, and then we can count how many times each value comes. Or for each bin, we could average what value of y comes up, and that would be a simple nonparametric predictor, which is basically on a histogram. And that would work well, actually, if there's only one variable and it's sufficient to break it into 10 different values. Because we would need to accumulate maybe 100 examples, and we would probably covering enough each of the cells in this discretization to give a decent predictor. And we could maybe extend this to 2 dimensions. So instead of having one variable, we have 2 variables. Now we'd have 10 by 10 configurations of interests. But if we have 3 variables, now we have 10 times 10 times 10 configurations of interest. And well, it's not so bad, actually. It's only 1,000 configurations. But you can see that it's growing fast. And if we only had 100 examples that were maybe enough here, it's not going to be enough here. There may be a lot of configurations that we don't see. Maybe some of them get a lot of examples, and most of them get 0 examples. And if we have not 3 variables, but 1,000,000 variables, well, we're totally dead. Even with 100 variables, we're already dead. So there are just too many configurations. How could we possibly generalize to new configurations we have never seen? That's the game of machine learning. How do we say something about configurations we've never seen? So the classical solution to this, well, the classical approach to nonparametric statistics is to say, to rely on smoothness. So in the 1D case, when we discretize the space, saying, okay, we're going to say that all the values between 2.5 and 3 are going to be considered equivalent, and we're going to be able to lump all those examples or average in some neighborhood, like with nearest neighbors. Basically what we're saying is we're saying the function we want to learn is smooth enough that I don't care about the exact difference between the value at 2.5 and the value at 3, because the function changes very smoothly. And in low dimension that works. But in high dimensions, what happens is that if I want to look at the little neighborhood of values that I'm going to average around, a neighborhood of examples that I'm going to average around, I'm going to end up with either an empty ball with no example in it, or a ball that contains almost all of the examples, and it's going to be useless. So it's something funny that happens in high dimension, that you can't just average locally and get something meaningful. Okay, so there's this notion of dimensionality which comes up, but actually if you dig deeper mathematically, it turns out that it's not really the number of dimensions. it's the number of variations of the function you want to learn. Remember, I said that these statistical methods rely on smoothness of the underlying function. And smoothness, basically, you can think of it, how many ups and downs are there? If it's linear, is very, very smooth. If it goes up and down just a few times, it's less smooth, but it's still very smooth. If it goes up and down a million times, well, then it's getting to be a complicated function. Actually, the kinds of functions we want to learn may be very, very non-smooth. So if you're trying to do computer vision, or if you're trying to do natural language or speech, the functions we actually want to learn are very complex. The number of ups and downs, or the number of different regions that we actually want to distinguish, could be very large. So a few years ago, we showed that the issue with the curse of dimensionality really is not dimensionality, it's the number of ups and downs. So in particular, many non-parametric statistical methods rely on the Gaussian kernel or some kind of similar looking Gaussian shape which is used to average in some neighborhood. And with these kinds of methods, we showed that the number of examples you need to get good generalization is proportional to the number of ups and downs of the function that you're trying to capture. So if it has 2k zero crossings, then you need order of k examples. And that's a problem, because if you have many dimensions, then the number of ups and downs could be exponential in the number of dimensions. But it doesn't have to be in high dimensions. You can have a one-dimensional function that's incredibly complicated, and it would still be hard to learn, even though it's one-dimensional. Okay, so the geometric view now that I introduced earlier, let me try to visualize it a little bit. So remember, Pascal told you about the training data as the empirical distribution, and he showed these plots, these examples as circles. So I'm going to do the same thing. Now, let's say you're trying to model the distribution of x and y here, or maybe you're trying to predict y given x. I don't care. The point is, you're trying to find which configurations of x and y here in that plane are likely, so that you can answer questions like, is this configuration likely, or is this configuration likely, or if I know x, which value of y should I use, right? These are the kinds of questions you're using machine learning for. Now, the problem is we know the answer at these points. We know these points are likely, which means we can answer about those points. But what about everywhere else in this 2D plane? So the smoothness assumption says the function we're trying to learn is smooth, meaning that if we know its value at some point x, we know that in some neighborhood, the value should be close. So if we know that the probability function should be high here, we could guess that it should be high in some neighborhood, right? So we could just draw little balls or little Gaussian kernels around each example. And of course, that's what many non-parametric statistical methods do. In this 2D case, it might actually work reasonably well. But of course, we're trying to think about what happens in high dimensions. And what's going to happen in high dimensions is that these balls are either going to be so large that they cover everything, or they're going to leave a lot of holes in places where there should be a high probability. So it's not going to be good enough. In order to really work out this data set, to make our solutions really generalized, what do we need here? We need to discover something a bit smarter about that data, that there is some structure, right? Where is that structure? Well, here we could guess the structure is that there's a one-dimensional manifold near which we have a high probability concentration. In other words, the points near that manifold have a high probability of actually happening in the data. So this is something we'll come back to a lot later in the week with other representation learning algorithms. The reason it's connected to the notion of representation is that if you think about it, this low-dimensional representation of the data, there is a low-dimensional representation of the data, which is the position on that curve, right? So we started here with a two-dimensional input, and I'm saying there's a concentration of probability in some region. So these are the configurations that actually happen more often. And if we could discover that representation, then that concentration, where is it that it concentrates, we basically solve our problem. But there's a way to think about this, which is if we could discover a new representation, which is a one-dimensional representation, or maybe just a two-dimensional representation, but we change the axes, right? So we can have one axis which is going to be the position on the manifold, right? And we could have another axis which is the direction orthogonal. So if you're here, you're some distance away from the manifold, that's one axis, and you are at some position on the manifold. So it's a change of representation. And you can see that under that representation, many things become easy. For example, of course, you can get the density very easily, because on one of the dimensions, you know, maybe this is the position 0 according to that dimension, and so everywhere at position 0 has a high probability, and everything else has a low probability. So that makes the density problem very easy. But it also allows you to do things like interpolate between examples more meaningfully, and maybe predict things more easily. Now you can have kind of what we've taken this manifold, which was nonlinear, and maybe in reality we're going to have manifolds which are very, very complicated. And by changing the representation, we essentially flatten the manifold, right? So in the new representation space, where one dimension is the position here and the other is orthogonal to it, it's like if we made the whole thing Euclidean again, and then we can do linear things in that space in order to make predictions and interpolate and do all kinds of fun things, right? So we turned a complicated distribution, which was, you know, this nonlinear manifold, into something that's flat and Euclidean, and we can do things like PCA and density estimation very easily. All right. So let me go back to this curse of dimensionality problem. What I've been trying to say is that if we only use smoothness, we're not going to be able to defeat the curse of dimensionality. And smoothness has been the ingredient in most statistical, non-parametric statistical methods. So we want to be non-parametric in the sense that we want to be able to have families of functions that grow in flexibility as we get more data. And neural nets are non-parametric in that sense, right? So they're parametric in the sense that if we fix the number of hidden units, we have a fixed set of parameters. But actually, that's not the way we use neural nets. The way we use neural nets is we allow ourselves to change the number of parameters by changing the number of hidden units depending on how much data you have, using a validation set, as Pascal was telling you at the end. So we have the ability to let our model grow with a number of examples. But we need to go beyond this smoothness prior. It turns out that with deep learning, there are at least two priors that are basically coming in for free. I'm going to now explain them. So one of them is basically coming under the name of distributed representations, and the other is basically about depth. And what I'll be telling you about is that these two priors have a thing in common, which is that there are ways to exploit compositionality and put it into our model. In other words, we're going to say that there's something about the world out there, the way that the world is generated. Remember, we're coming back to this notion of understanding how the world was generated and making hypotheses about how it was generated. But here we're going to make a very, very simple assumption that the way the data we're observing came up is by some composition of pieces. And the composition can be either parallel or sequential or both. So the parallel case is going to be the idea behind distributed representations, and that's what I'm going to be spending a lot of time in the next few slides. And basically, it's the same idea of, you know, feature learning, but I'm going to explain how it's making assumptions about the world. And the second is the depth. So in other words, we're going to have multiple levels of feature learning. And whereas here, it's going to be a kind of parallel composition. We choose this feature and that feature or that feature to be active, and we have a subset of features that are active to represent our input, a pattern of activation of features. In the case here, we're going to be not taking these functions in parallel, but in sequence. So we're going to have functions that are obtained by composing other functions that are obtained by composing other functions. And we get that with deep architectures, and we get that with recurrent nets. And so with these two things, as you'll see, we'll basically have added an additional prior or additional kind of intuitive notion of how the data came about, which is assuming some form of compositionality explains the things we're observing in the world. Any question up to now? Yes. 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 Okay. So there are different definitions of non-parametric, but the one that I like is one where we basically say non-parametric really means that we don't have a fixed parameter vector. Depending on the data we get, we can choose a family of functions that's more or less flexible. So a linear classifier is parametric because I can't increase the flexibility. Even if I get 10 times more data, I'm stuck with my linear model. On the other hand, with a neural network, if I get more data, I'm going to choose more hidden units and maybe more layers as well. So the family of functions that I'm allowed to choose from is not fixed a priori. It's actually growing depending on how many examples I get. And that's what non-parametric really means. It's not about having no parameters. It's about not having a fixed parameter vector, but allowing yourself to choose, the number of parameters that you need depending on the richness of your data. Is that answering your question?
So you mean you can choose a different number of layers, for instance?
Absolutely.
But for one fixed number of layers and one number of layers.
Yes, if you exactly. So what you have is a non-parametric family which uses as a building block a parametric family.
I like to say that non-parametric methods or families are those that have the highest number of parameters. An example of a nearest neighbor where the parameters actually being stored as a whole data set. It has a lot of parameters. That's considered non-parametric.
In fact, in many state-of-the-art say in computer vision neural nets, there are many more weights, many more parameters than examples. So we're talking about like millions of examples and hundreds of millions of parameters, typically. It's a very common situation. All right. Any other question? So yeah, before I get there, I show you this picture to illustrate that comes from Hong-Lak Lee, who will be speaking shortly, maybe in a couple of days, and Andrew Ng at Stanford a few years ago, which illustrates one aspect of multiple levels of representation, which is that these representations can capture kind of hierarchy of parts. So one way to get a composition of functions is to have functions that detect features like edges or parts of a face and compose them to get higher level objects or parts, right? So here what you see is that using these stacks of RBMs, they were able to have the first level units that detect edges. So they liked oriented contrasts at some locations. And at the next layer, they had units that preferred things like a nose or an eye. And the next level, they had units that preferred actually full faces in different configurations. So it's not exactly what is going on. There's much more to it, but it gives a glimpse of what multiple levels of representation could be, a parts-based hierarchy. But there's more to that. As I'll try to argue, an exponential advantage over methods that don't use this structure. Okay, so the methods that don't use a distributed representation are things like classical clustering, n-grams for language models, nearest neighbor methods, kernel, many kinds of kernel SVMs, most non-parametric density estimation or regression using local kernels. And so that's a lot of algorithms, and there's many more. Oh, also decision trees, for those of you who know about decision trees. There's a very simple way to understand what these algorithms do at a very high level. What they do is you take your input space. So we have the input space, and again, I'm doing a 2D thing, but you have to think this is in 1000D or 1,000,000D. We have the input space, and we're going to break it into regions. We're going to partition the input space. And for many of these algorithms, it's actually a hard partition like this. For others, it's something a bit more subtle where you have some kind of soft partition where you're allowed to know a kind of smooth interpolation between nearby regions. But basically behind this, you have a notion of regions. And the important point is that we're going to have a different set of parameters for each region. We're going to be able to tune what the answer should be in each region and where those regions are by using the data. For example, if you're doing clustering, maybe then we have some examples or some centers that correspond to the centers of these regions. And if you're doing one nearest neighbors, maybe every example is used to define a region. And in those two cases, you actually get some kind of Voronoi partition of the input. So you can think of how rich is the function we're going to compute here as related to how many regions there are. Because I'm able to change the output in each region depending on, say, how many points come here or what the labels are that are associated to each region, to the examples that fall in each region. So there's a notion of complexity that's tied to how many regions I have, the complexity in the sense of how rich, how flexible is my function. So if I'm doing nearest neighbor, I only have 3 examples, my function is going to be very simple. It's going to be some very simple partition. If I have 1,000,000 examples, I can actually represent something very complicated, right? Now, we can think in terms of sort of learning theory, ask the question, how are we going to generalize? And that's going to depend on the relationship between the number of examples I need and the kind of complexity I get, right? So what do I mean here? If I want to have a richer function, I'm going to need more regions, right? And to be able to define those regions, I'm going to need more examples. So for these kinds of models, there's a linear relationship between the number of distinguishable regions and the number of parameters, or equivalently, there's a linear relationship between the number of distinguishable regions and the number of training examples. I want more regions, I need more data, right? And the relationship is linear. And you might think that's the only way that is possible, unless I introduce some extra constraints or prior. If I don't know nothing else, that's all I can do, right? If I want to be a bit finer about what's going on in this region, I need more examples so I can split this region in 2 and have a different answer in these 2 places. Okay, but there's another option. And that other option is basically what's going on with neural nets and in general with distributed representations. So this is maybe one of the most important slides of my whole lecture. So please pay attention. So we are also going to define a kind of partitioning of the input space, but we're going to do it in a way that's incredibly efficient. We're going to do it in such a way that we're going to have an exponential number of regions at the price of a linear number of parameters. So we'll be able to say something about a function that looks very complicated in the sense that it has many ups and downs, many different kinds of values, many regions I can distinguish, and yet I don't need that many examples to learn it. Right? That's the magic part that Pascal was talking about. But it's no magic, as we'll see. There's a reason why this is happening. And it means something about an assumption we're making regarding the world that generated those data. It may be that these kinds of models, like what we have in neural nets, are not applicable everywhere to any random function. In fact, they're not. They work well in this universe, on this planet. Right. So let me go in a bit more detail. How are we going to do that? So the way we're going to get our regions, I'm going to consider a very simple case. You can have more complicated cases, but I'm going to do a very simple case to illustrate. We're going to have just one hidden layer of units. Like here, this is the 2-dimensional input, and let's say we have these 3 units, and I'm going to make these units as simple as can be. So linear classifiers with a 1-0 answer, binary classifier. So each hidden unit says 1 or 0, depending on which side you are of a hyperplane. So, the weights of these units and the bias together define a hyperplane in input space. On one side of the hyperplane, the unit says 1. On the other side, it says 0. Okay, so each unit defines a hyperplane, and now we have some configuration here corresponding to saying on which side of each hyperplane we are. So if we have 3 units, we could think we have 8 configurations. Actually, there are only 7 that exists because, well, because we're in 2D, but that's a detail. So what's going on here? We have more regions than the number of, well, if we extend this to higher dimension, we're going to have a number of regions that grows exponentially with the number of features, and so with the number of parameters. Because the number of parameters is the number of features times the number of input, whereas the number of regions is essentially 2 to the number of features. Now, if you actually have less dimensions than features, there's some correction for that, but it's still nearly exponential. In fact, it's exponential in the input size. Okay, so you can see that there, all the configurations of these bits that can occur. Some of them can't, but essentially, if we have the input size large enough, we can have an exponential number of regions. Okay, so compared to the situation we had previously, we had a number of regions that was linear in the number of parameters or linear in the number of examples that we need. Here, we have a number of regions that can potentially grow exponentially with the number of parameters and with the number of examples. So how is that possible? There must be a trick, right? Is it magical or there's a cheat? Well, every prior is a kind of cheat. It works for some things, but it doesn't work for everything. So you see that, those regions, I have these 7 regions here, I can't really choose their locations, and also, let's say I put a linear classifier on top of this, I can't choose the answers I'll get independently for each region. So there are some constraints about the kinds of functions I can represent. Not every function or not every partition here is feasible. Whereas in the other case, I could do any partition, right? It was a very, very flexible model. So this is going to work under some conditions. So let's try to figure out what those conditions are. And for this, I'm going to give you an example. Imagine that now the input is an image of a person, and that my 3 features are binary detectors, so they're going to have to be nonlinear rather than linear. They're going to be binary detectors that tell me if the person is tall or short. Maybe there's another one that tells me if the person is male or female. And maybe there's another one that tells me if the person wears glasses or not. Okay, so now you see that with these kinds of features, it makes sense that we can learn about each of those features almost independently of each other, right? I can train a detector. I could potentially imagine training a detector or having a machine discovering what wearing glasses means visually, and I don't need to see all the configurations of the other features for learning that, because detecting eyeglass detector is going to work. It should work independently of how tall the person is, whether the person is male or female. I mean, that might be some little interactions. Some females have funny glasses, maybe, but well, from my point of view, of course. So there might be some interactions, but mostly you can learn about each of these features independently of the other. And so you can see that, and you can have more than 3, right? You could have 1,000 of these features. You can see that the number of examples I might need to learn those features doesn't need to grow as 2 to the 1,000. It just grows like 1,000. The more features I put in, each time I add a feature, I don't need to double the number of examples I see. I just need to have, enough examples of that feature being present or not present. And so we get what we want, right? But it works because we're assuming that the world is arising out of the interactions of those features, that some say are 1, some are 0 for a particular example. And for any particular example, we just pick a pattern of these. And we can pretty much learn independently each of these features. If we were given enough the appropriate kind of data that covers their variations, we should be able to learn about each of these features more or less independently. So that's what gives us an exponential advantage, because now we don't need the number of regions to correspond to a number of examples. We can have many regions which are all the configurations of those features, and yet the number of examples is reasonable. It grows only linearly with the number of features. Do you have some questions about this? Yes. Well, I gave you a real-world example of an image with, that's the input, and the features are binary features which tell you something about the image. Right? Different aspects of it. Maybe different parts. So I talked about glasses, about the size of the height of a person, and you can imagine, you know, many more features. But the point is, if you imagine having, you know, somehow data that characterizes your distribution, and that covers maybe the two different values of each feature to keep things simple, that they're binary. They don't have to be. You don't need to see the configurations of all of the other features to really learn about each one. And that's different from the situation with non-distributed representations, where somehow I need to see all of the configurations of my pixels to be able to generalize. Here, the thing that's going to make me able to generalize is that I don't need to see all the configurations of those features to be able to make a meaningful statement, right? So for example, it could be that I've never seen 0, 0, 0 here, but I've seen the first feature being 0 alone. I've seen the second feature being 0 in some other configuration, and I've seen the third feature being 0, and maybe they just sort of add up to come up with some weights to come up with an answer about something you care about that maybe only depends on some subset of them or some linear combination of them. So that's what allows you to generalize, that you're able to say something about configurations of these features that you have never seen, because individually they keep their meaning. Like the meaning of tall person versus not tall person is something that remains meaningful whatever the other elements of the visual scene are. And you don't need to see all the configurations of all the other variables in order to be able to make sense of that feature. Yes?
So does this boil down to the assumption that the features are just independent of each other?
Well, they don't have to be exactly independent, but if they were in the right chosen way of formalizing it, yes, that would be really helpful. In practice, of course, they won't be exactly independent. As I gave in my example, maybe, you know, the female glasses and the male glasses are not exactly the same. So you actually need to see both of these. But there are many things about glasses that don't depend about whether, you know, how the style is. It's just the shape and where they are. And these things could be learned independently of the other configurations. Yes? Maybe I don't understand your question, but yes, there's some math that tells things about how many regions we get depending on number of features and number of inputs, and maybe that's not the question you are asking. Yes. Right. Maximum over what set? I don't understand what the maximum corresponds to. Maximum in what sense? Oh, I see what you mean. Yes, so we have an IPS paper, 2014, which studies fairly deeply these questions. And regarding the number of regions, what happens is that if you're not lucky, you might have, you know, coincidences that make some of those hyperplanes do nothing because, you know, they kind of align in a funny way. But the chances of this happening is like measure 0. It's very unlikely. So for most parameters configurations, you're going to get the maximum number of regions. Yes, and we can count that. So we have approximate counting arguments that give us bounds on the number of regions you can get. Yes?
So I see that if we're thinking on neural network, that this type of reasoning is very understandable towards the end where you go
Yes.
to categorize.
Yes, but I haven't talked about depth yet. So I'm only talking about the notion of distributed representation. So one layer. I'm going to tell you what happens now if you combine multiple levels. But even if you think about just one level of representation, you already get an exponential advantage here. So the number of examples you need to get a certain level of generalization might be exponentially smaller than if you don't use this prior. So if you just use the smoothness prior. Might be. In practice, we never see such an advantage, right? So if you compare like the best neural nets for computer vision and the sort of state of the art using, say, pure kernel machines, we don't observe an exponential ratio of the number of examples needed for getting a particular generalization. We get a big advantage, but it's not exponential, right?
My question was going to be actually like at another level, you get an exponential partition, but you're not allowed to act on it. Basically. Like if you start from a pixel level of images, you do get
Uh-huh.
this partition, but continuing onwards.
Right. So there's the question of what do we put on top of these features. So you need to have enough flexibility to exploit this representation. But the good news is related to what I was trying to explain about these manifolds. If this representation is really good, what it really is doing is it's unfolding the manifold. It's like a new coordinate system where things are flat. And if you have really flattened the manifold, then basically linear classifiers can do a good job. All right. Yes?
You talked about like these representations work on some of the problems. So isn't it good to kind of have a joint model where you use some good things from the parametric one, some from the non-parametric one, and come up with a joint model? Because over here you're learning a lot about the exponential number of parameters. These parameters can help the discrete model as well, and discrete model is optimized on some of the parameters which we learn, and that can help in this way.
Yeah, I'm not sure to understand your question. Yeah, there are situations where you do want to have the kind of flexibility that the classical non-parametric methods bring. And so there's certainly room to think about how to combine them in places where you need, for example, a lot of memory to store instances, right? So neural nets are really good at discovering representations that capture semantic aspects. Like, what is it that makes a cat be a cat? What are the features that makes a cat be a cat? But it's not very good at learning things by heart. If I want to remember about, you know, my cat, your cat, and his cat, and maybe 1,000 other cats, I might want to use some kind of memory-based, non-parametric type of model. So yes, there are certainly applications where you want to combine both. But the generalization comes from these representations. Yes?
So you present distributed representation as a fundamental advantage, but is it also a weakness as demonstrated by the adversarial examples? Because it seems very related, because like Gaussian models with local Gaussian areas, functions, or regions are not subject to the adversarial example problem. How do you see it? When is it an advantage and when it could?
Well, this is, I think, something we don't fully understand yet. The question you're asking about. First of all, the adversarial examples problem occurs for many machine learning. It's not really specific to neural nets. Second, but you're right that having kind of RBF units kind of limits this problem. But then if you have a model that doesn't suffer from, you know, these weird examples could actually happen, even though very rarely, or somebody could, you know, make them up. That's certainly something we have to worry about. But then not getting any good generalization is not good either. We first have to have good generalization, and then if there are issues, we need to fix them. So there's already some work showing that you can train with these adversarial examples and make the system a lot much more robust to them. But this is very, very sort of recent work, and we need more investigation in that direction. Yes?
So this is, from what I understood, is more of kind of a, not really a partitioning, but if you want the maximum regions, you just take all the possibilities of partitioning. But could you have like creating like some clusters on sort of like smart partitioning?
But that's what classical non-distributed representations do. They take essentially all of the regions that they can, given the data that they have. But they don't get any generalization out of this. In other words, if I give you a location in input space which you have no data, you're not able to say anything about it. Whereas with this approach, we're able to say something meaningful about configurations we've never seen before. And that is the essence of generalization. Okay, I should probably move on.
I'm a bit confused about what is different between this kind of representation with glasses, height, and I don't remember what was.
Yeah.
And one where you classify the pixels of the picture into black or white. This is also a distributed representation, right? You have this one
Right. Yes, except that the pixels are, that's right, except that the pixels are not a good representation. Because you can't learn about the distribution of each pixel almost independently of the distribution of the other pixels. They're very strongly tied together. Whereas here I can learn about, you know, what the relationship between the input and each of these features almost independently. So in a sense, we're kind of factorizing the distribution, saying the way it comes about is that we have these sort of independent factors, right, that explain what we see. And these actually are the kinds of things we talk about in natural language. Natural language was meant, I think, to explain those high-level factors that you know, from one person to another person, that explain the data. So the things we talk about that we put labels on tend to be explanatory factors. So whether the person is male or female, or has glasses, or is short, or has you know, long hair, these are things we've put names on because they help us making sense of the world. They are high-level factors, but not any. Huh?
Some kind of natural kind.
Yes.
Is not a natural.
That's right. That's right. Exactly. Okay, I should probably move on. So this idea of distributed representation was really at the heart of the renewal of neural nets that happened in the early 80s. That was called connectionism, or the connectionist approach. And two of the major players of this renewal are Jeff Hinton and David Rumelhart, and a bunch of others, of course. And they were kind of trying to present this way of thinking in contrast with the classical AI approach, which is based on the notion of symbols. The notion of symbol is something that's very natural when you think about symbolic processing of things like language or logic and rules, where each concept is associated with just a pure entity, a symbol. It's just something that's either present or not present. And there's nothing intrinsic about those symbols that, you know, define some kind of relationship between them. Whereas if we think about concepts as patterns of features, patterns of activations of neurons in the brain, then the concept of cat and the concept of dog can be related in the sense that they would share some features. So here I've tried to illustrate that by saying, okay, so I have some symbolic representation here, which is my input, or it could be an output, where there's, you know, what's called a one-hot representation, where I have a unit that says it's a cat, and the other units are saying other things like dog and so on, and it's either one or the other. But I also have a distributed representation, so a bunch of features that every concept can have, and the features for cat and the features for dog, so this is now the representation for dog and the representation for cat, somehow are close to each other because they share a lot of attributes. They're, you know, both pets and mammals and so on. And so we're now able to measure a kind of distance between those symbols, whereas between symbols there's nothing to say. They're all different from each other in equal ways. And this is something that's really important for deep learning and for neural nets, to understand this notion of representation of concepts of what may seem like symbolic concept to start with. This is something I built on with what's called a neural language model, starting with a NIPS paper in 2000, of which actually Pascal and others are co-authors. We built models of natural language, sequences of words, using this idea of a distributed representation for words. So the way we did this is we trained a neural net that has as input a sequence of words and tries to predict the next word. You could try to predict all kinds of things, but in that paper we just predict the probability for the next word being any one of the words in the vocabulary. So we have a large output layer with 1 unit per word in the vocabulary, and we have also very large inputs where you have a 1-hot representation for each word in the input window. So it's not a bag of words representation like Pascal said. Instead, it's just a 1-hot vector for each position. And the crucial part here is that the first layer of that neural net is just a mapping that's learned that projects these symbols, these integers, into a distributed representation, which is just a vector of numbers. And we use the same mapping for all the words, independent of their position. Of course, each word in the vocabulary gets a different mapping. And these mappings are things that we can visualize by two-dimensional projections, usually nonlinear projections. And we see clusters of words coming up that are semantically similar. So if we zoom in and zoom in again, we see things like, countries having their vectors, their word vectors, their distributed representations being close to each other. And this is not something that was built in. It just discovers these representations that have these properties. Or maybe verbs come close to each other, or conjugations of to be come close to each other. And even more exciting is that these vectors somehow have dimensions that are learned, that is completely discovered from scratch, that are meaningful, and whose meaning is preserved across space. So you can do some kind of arithmetic with those vectors, simple arithmetic, and it will allow you to do things like reasoning by analogy. So for example, if I take the vector for France and I subtract the vector for Paris, I now get a new vector which is pretty much aligned with the vector I get by subtracting the representation for Italy from the representation from Rome. So these two difference vectors that are almost the same, they represent the meaning of the capital of a state. And you can do the same game with many pairs of words. So if you take king minus queen, you get a vector which is almost the same as man minus woman. So why is that happening? This is, initially we were very surprised about this, and it seems almost amazing. But it makes a lot of sense. So if you think about the pattern of activation corresponding to king and the pattern of activation corresponding to queen, they should be almost the same in most dimensions, except for what has to do with being male or female. And if we're lucky, maybe there is an input dimension that corresponds, maybe a bit that says this is the male version of the concept, or it's the female version of the concept. And of course, the same bit would be present in man and woman would have all of the same attributes except for that bit. So now when we take the difference between those two vectors, what remains is just that bit. And we take the difference between those two vectors, again, we get the same bit. Now in practice, it's not going to be a particular axis-aligned direction. It's going to be a vector that's not a one-hot vector. But it's the same concept. Right? So we are learning these representations that are, because they're used to try to capture the distribution of the data, tend to discover meaningful aspects of the world that are like the underlying factors we may think about that can generate the data. And because that happens, we get amazing kinds of generalizations, like in this example. It's not just these kinds of toy examples. These kinds of models, of course, are used in practice for solving many problems. All right, I should move on to talk about depth. So I said that having a distributed representation gives you an exponential advantage, at least up to an exponential advantage. But there's another source of exponential advantage, which can be obtained on top of what you get with distributed representation, which is having multiple levels of representation. So that's deep. So to explain this, I first need to tell you a little bit about some of the history here about representations. There's a lot of misunderstanding about what depth brings that I'm going to try to dispel here. But before I get there, one reason why depth was not studied that much before this century is that many people thought that you don't need a deep neural net. A shallow neural net with a single hidden layer, in theory, is sufficient to represent any function. And it's not just neural nets. You can have 2 layers of logic gates, for example, is sufficient to represent any Boolean function. Or an RBF network with 1 layer of RBF units is sufficient to approximate any function. Assuming you have enough of these units, enough hidden units, you can approximate any function with a required degree of accuracy. And we call this property universal approximation property. But what these results don't tell us is how many units will I need. So it may be that with a deeper neural net, we could represent the same function that we could also represent with a shallow one, but more cheaply, with less units. And in fact, there's now a series of results showing that this is true, and that there exist families of functions, and fairly large ones, for which you can get an exponential advantage. So the number of units or the number of parameters you need can be exponentially larger if you have only a shallow network than if you allow yourself to have a network that's deep enough. Now, how deep? We don't know. It depends on the function you're trying to represent. So presumably, if you're trying to represent a function that's very deep, in other words, that the true function needs many levels of composition to really be represented properly, then your neural net needs more layers. But we don't know ahead of time how many layers you need. One thing I want to mention is that actually depth is not necessary to have a flexible family of functions. So people think that if we have deeper networks, that means that they represent somehow corresponds to higher capacity. But actually that's not necessarily the case. You can still roughly think about the number of free parameters as representing your capacity. So deeper doesn't mean you can represent more functions. It's just that the set of functions that you can represent has a particular characteristic. It has this characteristic that it is obtained through composition of many operations. And if the functions you want to learn have this characteristic, this property, then you're much better off approximating these functions with a deep neural net. There's some other analogies that help you understand depth. So first of all, there's the notion of reuse. So in a deep neural net, we are reusing the lower layer features to produce the higher level features. When we write a computer program, we don't usually write a main program with one line after the other. Typically what we do is we have subroutines that we reuse. So you can think of what the hidden units are doing as kind of subroutines for the bigger program, which is what you have at the final layer. So that's one way to think about it. Another way to think about it is that actually when you run a program, it's a sequence of operations. So if you have a program that has 10 lines, you can think of it like at each line, let's say it's Python code, at each line you're doing some computation, and the result of that computation is changing the state of the machine to provide an input for the next line, right? So the input at each step of the computation is the state of the machine, and the output is a new state of the machine. So that's the Turing machine, right? So the number of steps that a particular Turing machine executes actually corresponds to the depth of computation. And so although in principle you can represent any function by having a program with 2 steps, it's not going to be a very interesting program. It's not going to be, it's going to be able to compute anything, but it's not going to be able to compute interesting functions efficiently. So how would you have a program in 2 steps, in 2 lines, that can output any function with some precision? How could you do that? How could you have a 2-step program that can represent any function? It's a riddle. Lookup table, thanks. That's what a SVM, kernel SVM does. It's a lookup table. A shallow neural net is kind of a lookup table as well. So lookup table, first line, you know, get the content of some at some address in your lookup table. Second line, take the result and you know, do something with it, maybe multiply it by some number and output it. Okay, so we need deeper programs. There's another analogy that I sometimes use that helps to understand this notion of reuse. So most people being trained in a bit of mathematics understand polynomials. So let's think how you could represent polynomials. You could represent polynomials by writing out the polynomial as a sum of products, right? That's the usual form. But you could also write it as a graph of computations where each node performs an addition or a multiplication. So this is what I've chosen here. And now if you do it this way, you're going to have kind of deep computation where you could represent a polynomial that has an exponentially large number of min-terms, of these terms if you do the sum of products, even though the number of computations I'm going to do, the number of additions and multiplications could be small. So why would that happen? Well, because I can reuse some operations. Like, let's say I have this node that multiply x2 by x3. Because its value is going to be used in both of these 2 nodes and then combined later, this product x2, x3 comes up in the polynomial associated with that later node in many places, like in 4 places. And so even though I have you know, maybe an exponential number of these products coming up later, I needed to do this product x2 times x3 only once, right? So this is I guess an illustration of that same idea, and there's some theory, you know, that's connected to that. I mentioned this result from our last NIPS, which basically shows a very large family of functions. For large families of functions, the result I was telling you about with an exponential gain, both for a shallow neural net and for a deep neural net. So these are rectifier networks or piecewise linear networks, so that includes things like maxout. And turns out that these types of neural nets are very, very common now, so this is a fairly large family of functions. And this paper is about counting number of regions, exactly what I was telling you about before, but doing it in a very formal way. And so it basically shows that with a single hidden layer, you get an exponential number of regions compared to exponential in number of hidden units, right? Or inputs. It depends on both. And if you have more layers, then you can get another exponential gain. Okay, so I'll let you look at these if you're more into the math for these things. The last bit of sort of motivating theory I want to talk about is not about an advantage, but about a belief that seems to be wrong about a supposed disadvantage of neural nets. So one of the reasons why neural nets were discarded in the late 90s and early 2000s was that the optimization problem for neural nets is non-convex, meaning that there could be lots of local minima. In fact, since the late 80s, early 90s, we know from theory that there are an exponential number of local minima in neural nets. And this fact, combined with the success of kernel machines in the mid-90s, late 90s, sort of played a role in kind of greatly reducing the interest of many researchers in neural nets. But this was relying on the idea that if we have many local minima, because the optimization function is non-convex, then we're in trouble, and for sure we're not going to get any guarantees about finding the optimal solution, but furthermore we might be stuck in very poor solutions. Well, something changed very recently, so over the last year. we now have evidence both at the theoretical level and empirical level that this issue of non-convexity is actually maybe not an issue at all. Or at least it changes the picture we have of the optimization problem with neural nets. So if you're interested in the optimization aspects of neural nets or deep learning, I encourage you to look at these papers. So there's, we presented this for the first time in 1 year ago, roughly in the spring. Then we had a NIPS paper, and then the group at NYU with Anna Choromanska and Jan Lequin presented a different kind of perspective on the same problem, which essentially comes down to the same kind of conclusions. So let me try to explain a little bit what these papers say. They tell us about saddle points. So let me explain a little bit the picture of the optimization problem in high dimensions versus low dimensions. So if we are in low dimensions, which is the kinds of things we mentally visualize, you're going to have a lot of local minima, right? If I draw a random one-dimensional curve, it's going to have lots of ups and downs. And here's a random two-dimensional curve, right? So a random curve in two-dimension typically has lots of local minima, and with that kind of picture, we think that local minima are going to be a big problem. But it turns out that in high dimensions, local minima are not really the critical points that are most prevalent in most of the places of interest. So let me try to explain what I mean. Basically, when we optimize our neural nets or any high dimensional functions, for most of our trajectory as we optimize, the critical points, in other words, the places where the derivative is 0, that we're going to come close to are going to be saddle points. So what is a saddle point? They're not going to be local minima. So we're not going to be trapped in local minima. We might have trouble escaping saddle points, but we can always escape saddle points. So what is a saddle point? So there's a picture here. Again, in 2D, but in general, so what is a critical point is where the derivative is 0, so the function that is flat in some place. And then, well, it has to go up or down in different directions. So here you see it's going up in these directions, but it's going down in these directions. And that's a saddle point, where there are directions where it's going up and directions where it's going down. A local minimum or a global minimum has all the directions going up. A local maximum has all the directions going down, right? You can't go higher locally, and same thing for the local minimum. So what's going on here is that intuitively, in a very high dimensional space, so the space of parameters here, if you think about a saddle point, the number of directions where it would have to go up to become a local minimum would be all the dimensions, right? So if somehow there's something like a kind of randomness in how these functions are constructed, and you independently choose for each direction whether at the critical point you're going up or down, well, you can see that it's going to be exponentially unlikely that all the directions go up, except if you're near the bottom of your landscape. In other words, you're near the global minimum. Because of course, when you have a minimum that's near the global minimum, you can't go further down, so all the directions have to go up. So that's kind of the intuition. And so what happens really is that you have local minima, but they are very close to the global minimum in terms of their objective function. And there are some theoretical results from statistical physics and matrix theory that suggests the following: that for some families of functions that are fairly large, like those that you get by Gaussian processes, there is a tight relationship, a concentration of probability, between what's called the index of the critical points and the objective function in training error. What is the index? The index is the number of is the fraction of directions that that are going down. So you have, say, at a minimum, all of the directions are going up. So you have 0% of the directions that are going down, and that's a local minimum. So when the index is equal to 0, you have a local minimum. When the index is equal to 1, you have a local maximum. Anything in between, the fraction of directions that are going down, is something in between. You have a saddle point. So local minima are kind of special cases of saddle points where the index is 0. Okay, and so what this theory says is that if you think of the joint distribution of index and an objective function, distribution because we imagine a large distribution over functions that we're trying to optimize, there's going to be a concentration of probability on some curve, meaning that for a particular training objective, most of the critical points are going to be saddle points with a particular proportion, a particular index. And we can do empirical experiments to verify that, and so that's what we did, and we find that indeed you have a kind of tight relationship between index and objective function. Okay. Yes. Right, we don't. So these, you can always imagine constructing an objective function that is hard, that has bad local minima in the middle of, at high error. So that's, you can build it by hand very easily. You can place the local minima in bad places. So the question is whether these families of random functions that can be studied theoretically like this are representative of what we have with neural nets. And we don't know the answer to that. But we've done some experiments. So like this experiment is on real neural nets, where what we do is we launch a bunch of experiments where we train, and along the way, every once in a while we look using very expensive methods for the nearby critical points. And then we use like Newton's method to find the index, like how many directions does it go up, compute the eigenvalues of that the Hessian at that location. So it's only an empirical validation, and we probably would like to have more such experiments to verify that that statement is true. So that's why I'm saying we have no proof that this result applies to the kinds of neural nets we want to optimize, but we have some evidence that the behavior we are getting corresponds to what the theory suggests. And of course, the theory makes assumptions which we don't know are true. Yes?
So on the practical side, if we get more evidence to support that neural networks use this kind of function, does that mean that there's no much point in using anything else than gradient descent?
Maybe, maybe not. So even though we may not get stuck in local minima, we might get stuck in regions that are, or near regions that are flat, or some other complicated shape of the objective function which makes, say, stochastic gradient look like it's stuck. In theory, if you wait long enough, SGD will escape so long as there's no local minima, SGD will escape. But it might take so long that you won't see it. And we have lots of observations. So let me show you in the next slide. So we have lots of observations where we see things, and people who have played with neural nets sometimes see this, where you see the error go down, and then it seems to plateau. And maybe if you're lucky, something happens, and then it goes down, and then it plateaus. But let's say we had stopped the experiment here. We might think that this is the best we can get. Actually, something else is going on. It looks like we are approaching the region of a saddle point. The gradients are not approaching 0. We don't understand why, but there's no progress of the objective function. It's kind of bouncing around, not finding the escape route. My intuition is that this is such a high-dimensional space that there's only a few dimensions where it's going down, and somehow it's not finding them, maybe because of curvature problems or all the things. But so what I'm saying is, yes, it's worthwhile to continue exploring optimization methods beyond simple gradient descent. But maybe we need to take into account the fact that what we're finding is not local minima. It might be something else. It might be something classical, like differences in curvature, or something more subtle. Yeah, so we can measure those in. Yeah, that's right. And in fact, what you find is that as you go lower down, you see here in this picture, it spends more and more time on these plateaus, right? They get harder and harder, presumably because there are less directions going down. Yes? I don't. Stopping criterion is how much do you want to spend in time, right? So I remember people are getting lazy these days. They'd like to have the experiments finished in 2 days or something. Or when I was a PhD student, we were willing to wait like for weeks. And that was not enough. I mean, in retrospect, if we had known, we should have waited for like 2 years, and then we might actually have, accelerated the progress of research in neural nets, because people discarded these things in part because we didn't train them long enough to get the kinds of results we are able to get now with GPUs and much faster hardware. Yes? I believe it's an autoencoder task with either letters or MNISTs. So that's in the NIPS 2014 paper. First author is Yann Dauphin, so you can find all that information there. Yes, Orvik. It's very expensive to actually compute that. So it's not something practical, right? So we can do long experiments where we measure these things, but, All right, I'm going to just use the last few minutes quickly to tell you about other priors that come into many deep learning approaches, especially some that use unsupervised learning. But a lot of that will have to wait for either my lecture at the end of the summer school or other lectures that will talk about these concepts. But to get you motivated, one interesting observation is that humans, and especially striking with children, are able to learn a new task, like the category of a new object, from very few examples. Sometimes just a handful, sometimes one example. If you think at it from a statistical learning point of view, it doesn't make any sense, right? We can't possibly have meaningful generalization, even using a deep net, with a single example. The only way this can happen is because the child is using accumulated knowledge from previous learning. And that knowledge could be, used to build representations such that in the new representation space, things are very, very easy. Like a single, prototype buys you essentially, the characterization of this new category. One other way to think about it, which is even more interesting, is that if you've built a mental model of the world that basically understands how the world works, and now you give me a new category, you say, here's an example of blah, blah, blah. Because you understand how the world works, it's obvious what blah, blah, blah means, right? And now you can generalize to other instances. So, an example of blah, blah, blah could be, oh, I'm going to teach you a new game. Here's an example of how we play it. And we do that all the time. So for this to work, you need more statistical assumptions. That basically the way the world works now, for these new examples, is the same as the way the world worked for the other tasks that I solved before, or maybe the unsupervised learning I did from all of the examples I've seen before. So we need to introduce more priors beyond the ones that we talked about with distributed representations and depth. For example, we would like to use the following prior, that the underlying explanations for the x's that we see now in the context of having to predict a y are the same as those that are behind the data we've seen before, from which maybe we've learned by unsupervised learning to characterize the distribution of the past data. So if the same factors explain x when we see it alone, and the relationship between x and y in supervised learning, then we're in business. Then we can hope to actually get very fast generalization. This is called transfer learning, or between tasks, or between unsupervised learning. Okay, so I guess many of you have heard about the idea of semi-supervised learning. In purely supervised learning, we're just using the labeled examples, and here maybe is what we do. But if somebody gives us these other unlabeled examples, we would probably choose something like this linear classifier. So we need to discover something about the input distribution in order to do that. Another example of sharing that's very, very common is multitask learning. So the most common case is, say we have images as input, and there are different questions you'd like to ask about these images. And it may be that the lower levels of a deep net can extract features that are useful for many of these tasks. If there is this kind of sharing of underlying factors that is applicable to many of these tasks. In other words, there are some underlying factors and that explain the variations in x and explain some of the tasks, and different tasks basically maybe look at a different subset of these factors in different ways, then we can gain a lot by training our models with this in mind. For example, we could use the same neural net except for the upper layers that are task specific. So that's the most common setup. You can also have some kind of multimodal approaches where you say, okay, I'm going to have representations for different types. So this is actually what is used in Google image search that was built by my brother Sami at Google and by collaborators, where we're going to imagine that there's a representation for images and a representation for queries that go in the same space. And by learning these two representations together, we can generalize in pretty amazing ways. More generally, you can imagine that you have, say, different modalities like x and y. We learn a representation for each modality as well as a kind of translation between them that tells us how to go from one to the other. If we try to learn this directly in x and y, it's hard. But if we do it in the right space, things become very easy. That's the hope. Another similar case is, well, like speaker adaptation or writer adaptation or other kinds of cases where the sharing is near the input, not the output. Maybe we want to do speech recognition and we want to have a different kind of transformation, maybe depending on the noise, depending on the person who's speaking. So we can share the upper levels here. So there are many places where you could share. All right. Let me see. There is one idea that I would like to end with, which is connected to many things I've been saying, and to some work done by some of the leaders in kernel machines that have been working on causality recently, Bernal Shopkoff and his group, that I think give a kind of intuition as to why unsupervised learning could be helpful. The idea is the following. Imagine we have our inputs x and the labels y that we're trying to predict. And now think about the causal relationship that could exist between these, say, images and labels. Well, there are two basic possibilities. One is that x is a cause of y, or x is an effect of y, right? So which is the cause, which is the effect? Of course, it could be complicated, more complicated than that, but let's imagine just these two cases. Well, it turns out that if y is one of the causes of x, then doing unsupervised learning is going to be very, very helpful. But if it's the other way around, that y is an effect of x and x is the cause, then unsupervised learning is useless for the purpose of semi-supervised learning, right? And so it turns out that in most of the AI tasks, the Y's are things like words that we like to talk about the world, and the X's are things we measure in the world. And our brain is trying to make sense of the world, so we created these labels, these concepts that we talk about, that are our best ways of characterizing the things we observe, and that probably means essentially a way to talk about the causes of what we observe. And so it works. It works because in the real world, the things we want to predict are the things that humans like to predict, the things that humans talk about. And then it means that there is the right kind of causal relationship between the x's and the y's. And the effect of that causal relationship is that if you look at P of y given x, then the right way of modeling it, the one that will have the greatest statistical power, is basically involves capturing P of x given y and P of y. And because P of x through Bayes' rule is just the sum over y of these things, the right P of x, the one that will work the best, is the one that really involves introducing the y's as an explanation. So let me give you a very simple example of that, if I can get this to work. And yes. And yes. So imagine that the world is very, very simple. It's just a mixture of two Gaussians. So this is x, and this is P of x. And this is y equals 0, and this is y equal 1. But you don't know. However, you do see the data. You see the x, and you see that there are two natural classes. And because the data really was generated with y as one of the causes, the way you'd think the data was generated here is somebody first picked the y, and then given that y, you have a Gaussian distribution. That's the right way of modeling that data. Now, of course, in the real world, the relationship between x and y is much more complicated, but it tells us that even if we don't observe the y, if we model it the proper way, we're going to see emerge as a natural random variable that explains it, these labels. If it turns out that these labels are the kinds of things we want to predict at the end of the day, then we are really in business. So that's what's going on. All right, thank you very much.